So this talk, first of all, I'm Sam Skillman. I'm at University of Colorado. I'm one of the Y2 developers, and you won't see as many pretty plots in this one, but this is really a talk to see how you dig into your data if you really want to get at the numbers and start moving around within your data and examine your simulation. So what we're going to cover is we've seen how to do peak value stuff a little bit. I'm going to explore a little bit more on that type of operation. Then we're going to look into how you inspect the individual cells, talk a little bit about derived quantities, and show you some simple code for doing fairly complex operations with only a few commands of YT. So first of all, we're going to look at locating the max value. You've seen some of this already a few times. So you just go through, and that's a little bit small, but hopefully you can all read it. So you load up your data set, and you can find the peak density value using the pf.h.findMax, and you can print that value and its position. Is there any trick to actually getting this laser to point? Anybody? This one? Ah, okay. Okay. Okay, so you guys have done this a few times, so I'm going to assume that you've made it through there. And what you should see is this basic printout from what we've seen already a few times, and it's just printing out the max value here and the position in code units. So now that you're there, what can you do? Well, you have this value and this position. You can use a different tool hanging off the hierarchy called pf.h.find field value at point. And so now I'm going to take that position that I had just found in the previous command and say, give me the field value of density at this position. And then go on and give me the temperature at that position. And then do something tricky where I get the density, the temperature, and the x velocity all at the same time from that position. So I'll let you guys have a few seconds to enter that kind of stuff in. And it doesn't really matter to me which data set you use. I'm using one of the ENSO 64 data sets. You could use the ENSO Tiny Cosmology or a Flash data set of your choice. All of these things should be fairly fast. Oh, sorry about that. Let me make sure that doesn't happen again. Okay, is anybody still working on this type of operation? I see a few eyes still reading, so I'll give you a few more seconds. This, you don't necessarily need to do all these things in a script and then run that. Feel free to just load this up interactively. Just open up a IPython or just a Python terminal. Feel free to grab any other fields that you might actually care about in your respective data sets. Yep, in this last example, I'm passing a list of density, temperature, and x velocity, and it's just going to accept that and give you all three values at the same time. Everybody pretty much there? Anybody still need to see this screen? Okay. So if you choose a position that's not the center of a cell, it'll just grab whatever value that is from that cell that that point is within. It's not going to interpolate any of the values to that point or something like that. So it'll just be the cell that that point, the cell that contains that point. Okay, I'm gonna move on here. So what you should see is something like this. You see the normal things, the information from when you run YT. Here it's showing you the peak value or peak value of density and the position. Remember that first time we said get the density back, and that shows you that it's getting the same value as it gave you in that find max calculation. Then you ask it for the temperature, it gives you this 1.3 times 10 to the 7 or something like that, or maybe 10 to the 8. And then when you say get a few fields at the same time, that actually prints out a list of values corresponding to the density, temperature, and x velocity, all in CGS units. Is everybody good to go on that? Anybody not understand what happened or have something go drastically wrong? Yep. Yeah. That is in that case that position value is a NumPy array, I believe. For those, I believe all you have to do is give it either a NumPy array of 3 or a list of 3 floats. Okay. So, we're talking about this access to the grid quantities and the cell quantities here. You may want to know which grid you're actually in and try to access that grid. So now we have the same stuff as above, and we've added a few things on here. And now I'm going to use this new command, pf.h.find max cell location, and find it on the maximum of density. You could put any field you want in there. But what this returns is a list of 4 values, the first of which is the grid, then the cell, the value of what it found that maximum density to be, and the code unit cell position. So what it does then is print out that grid, that cell, value, and position. But the main point of this is you don't have to necessarily copy and go through quite all of that, is that you're able to go through and get the actual grid object that YT has created, and then you have access to that grid and everything it contains, like the data and any properties along with it. Because you can do that, you can then take that grid and say, give me the density field of that grid. That'll return some, in this case, 3D array of density values. And use the cell that you return for me to give me that exact value at that cell, which should be the same as the peak density that we got a while back. So you're saying, and then the next thing is take the temperature field instead and give me the value of corresponding to that maximum density cell, where a cell is now a 3 array of ints, which you'll see coming up here. So in interest of a little bit of time, I think I'll just move on and show you the results of what happens here. So most of this is old. Then under the find everything, it shows what this grid is. This is Enzo grid 107, number 117, basically, just the name of that grid. The cell value, so it's in the 757 cell of that grid, is where it found that max to be. The value, the position, and then again that when we asked for the grid density and the value of that particular cell, and then the temperature, that's what gets printed out later. So this gives you an idea of how you would access a particular grid and access the values within that grid of a particular field. Does that make sense to everyone so far? Does it not make sense to anyone? Okay. So now we're going to move a little bit to a different topic called derived quantities. This is stolen from Matt's intro slide at some point. And a derived quantity is a reduction of a field, a combination of fields, or other information to a fixed number of outputs. This means that in practice what you take is some YT object, perform computations on that data within that object, and return a final value. Types of these derived quantities are things like, say you have an object like a sphere, you want to calculate the total mass, or you want to calculate the center of mass. We also can do angular momentum vectors, bulk velocities, a total quantity of some other field that you can choose, and then weighted average quantities. There's a whole list of it on the YT docs, of course. So here's an example of some simple derived quantities. In this case, I'm loading up a somewhat larger Flash data set, which is the Galaxy Cluster Merger data set. Feel free to pull from the gas sloshing data set if you prefer. That goes a little bit faster. And what I'm doing here is, after I load up my data set, I'm going to grab all of the data within that data set. So I'm going to say AD is pf.h.all_data, and that'll return all the grids so that you can access quantities about the entire data set all at once. Yep. That's so. It will, when you are acting upon this all data, it will only calculate any values that you ask for based on the most refined data, and that's true throughout whatever any code that you're using. So when you ask for, say, total mass, it's only going to sum up the mass in each cell at the highest refined level for that given region of space. You should probably replace this one with gas. What is it? Sloshing? Gas sloshing. I was making this a while ago based on this data set, so. So what I'm going to do with that all data is I'm going to say, first, what are the kind of quantities that are available to us that we can query about this data? And I'm going to print those out. And then I'm going to say, get the bulk velocity. And so out of the entire data set, what that's going to do is create an average, a weighted sum of the velocity times the mass. And so it gives you the average velocity of the entire data set. How's everybody doing on getting this in there? Does anybody need to see this slide any longer? Okay. So what this shows, first when we asked it what kind of average quantities are available to us, we can see that there's these same derived field lists that we could have looked up on the docs that I mentioned a minute ago. But it's min location. If there were stars in this data set, you could calculate the star angular momentum vector. You can get the total mass, the angular momentum vector, some total quantity. In this case, we just said, give me the bulk velocity. And it went through, and for every cell in the data set that's at the maximum level for that region of space, calculates that bulk velocity, and here's the final return result. So a very simple way to act on your entire data set all at once. Now, we're going to add along to what we were doing there and show what you can do by, in this case, we're going to grab the total mass. And then you don't necessarily need to write this down because I'm going to show you what this does immediately, and I think you'll be able to understand what's going on here. These scripts, by the way, as well as all the other scripts, will be available later online. So in this case, I'm going to get the total mass, and then I'm going to do some Python trickery to try to get all the values that I possibly could from this data set in as easily as I can. So what I'm going to do is look at the keys in the quantities. Keys just means out of all the dictionary, what are all the keys that I could ask for? So that's what we printed out earlier. For each of them, I'm going to try to print the key and the quantities associated with that key. And if it somewhere fails because I'm either not giving it enough inputs or anything else, it's going to just say unable to calculate that particular quantity. And so what this does... this stuff? Sorry, this is to reduce some of the output that YT says at the beginning. All the info and debug information that YT prints out. You can override that so that it's a little bit more quiet. And so what this does is it's going to attempt to get them all. It failed to get min location because min location asks for a type of particular field to calculate that minimum value. But then it gets the, and it also doesn't get the star angular momentum because there are no stars in this particular data set. But it does calculate the total mass. It calculates the angular momentum vector of the entire data set. Total quantity fails because it needs a field to actually ask for that. Finds the center of mass, finds the bulk velocity. It's unable to calculate a few of these because, again, it didn't specify all the needed parameters. And then it calculates this baryon spin parameter, which is something to do with halos, which doesn't really apply to this simulation. But this was just to show the types of quantities that you can look at. Feel free to go through the docs and look at what each one of these types of derived quantities does. But the main takeaway with these is that these allow you to calculate bulk properties of your data and your simulation very quickly and very easily. So now what we're going to do is don't bother going through this because you get very little in return for typing a lot, but just try to follow along here. This time, instead of taking from all of the data in the box, we're going to first create a sphere object by saying, give me a sphere of radius 5 megaparsecs centered at that central position that we first found. And then I want you to give me, for that sphere, give me the weighted average of temperature weighted by cell mass. And so now, instead of calculating that over your entire data set, it's only going to use the data within this sphere object. So after you create that object, the syntax is the same. You just say quantities. In this case, it's the weighted average quantity. Give it the first field that you want to find and the weighting. And then we're going to print that average temperature. And so in that case, I've just shown the results in line here. And this is the only piece of information that spits out. It tells you that the average temperature is 3 times 10 to the 7 Kelvin. So you can do this with any data object that YT can create. You can use spheres, disks. I think there will be a later talk about more complicated objects, data objects. But you can use the same syntax after that once you have the data source to grab all these quantities. Does anybody have any questions about this so far? Okay. Now I want to also show that you can do these same type of quantities based on particle data. Again, you're not going to get a whole lot in return for typing all this stuff out. But I'm going to create another sphere, this time 10 megaparsecs, just kind of arbitrarily. This time I'm using the ENSO 64 data. I'm going to grab all the particle masses of the particles in the simulation by saying, or sorry, in that sphere, by asking for that sphere, which is a data object, and then just giving the key particle mass. Then I'll show you on the next slide what that looks like. It'll be the number of particles and the total mass of the particles by calculating that sum. I can do this dot sum because this particle mass that I'm going to get is a NumPy array, and that dot sum operation can be done to any NumPy array. Then I'm going to show you that by using the dot quantities, I can do the same calculation, and we should get the same value. So when I say I want the sphere quantity of total quantity particle mass, it should sum up all that particle mass, give me the same as when I grabbed the data itself and did the sum myself, in a way by passing it through NumPy. And so you grab that sphere, it has 3,000 particles. The total mass of those particles, by just taking the data that it returns to you and doing dot sum, is 5 times 10 to the 48 grams, I guess, in this case. Then when you use the dot quantities, lo and behold, it gives you the same total that you got by doing the sum yourself. So now many pieces of information are quickly and easily available to you, especially when we combine what we've learned so far. So I'm going to show you a slightly more complicated example. It says, what if you wanted to calculate how kinetic energy evolves in your simulation? Now, later on in this workshop, we're going to talk about things like time series and learning how to loop through your data set for an entire simulation. But this is going to show you a kind of quick and dirty way to get these quantities from your simulation. So what I'm going to do here is I'm going to be examining the ENSO 64 data set. It will run quite a bit faster if you use the ENSO tiny cosmology, but I did this a while ago. So I'm going to give it a name pattern here. This is just a string that says that all the data that I'm going to care about follows dd and then 4 integers and then /data 4 integers. Then I'm going to create some empty lists of kinetic energy and the current times. And then I know that there are 44 data dumps in this simulation. So I'm going to loop through those and say, load up a parameter file. I'm going to give it this name pattern and feed it in the data set number that I'm on. So it's going to put the value of whatever I is into these 2 integers in the name. So it's going to load that up. It's going to grab all the data for that simulation. And then it's going to calculate the total kinetic energy. So it's going to ask for the all data.quantities. In this case, I'm going to do a weighted average of the kinetic energy weighted by mass. Now, this may or may not be useful for you in terms of what your simulation is. In a cosmology simulation, this doesn't give you a whole lot of insight, but maybe if you were doing a turbulence simulation or a shock tube, I don't know, anything else, it might be something that you might actually care about. I'm going to grab the current time off the parameter file, and then I'm going to append each of these values into these empty lists that I've created before the loop. Then I'm going to use matplotlib to manually plot these values. So from up here, I've imported matplotlib.pylab as PL. And I'm going to do a semi-log plot where the y-axis is log space and the x-axis is linear space. I'm going to give it that times list and the kinetic energy list and put some labels on it. So you go through that. If you actually run something like that on this data set, it takes maybe 10 minutes or so. ENSO tiny cosmology, I would assume it would be a minute or 2. And what you get out is the average kinetic energy as a function of time out of your data set. And so now, if you go back and look at that, there's a few lines in there that I didn't even need. I could have appended these values directly into these lists. But the point is, with a very few number of lines of code, I've created a result that might actually be, a plot in one of your papers. So I don't know how much we actually learned from this particular plot, but Sure. So in this case, the dot quantities, you give it a, let's see, dot quantities is a, yes, okay. And so dot quantities is a dictionary. So if you just looked at what this is, it's going to return to you basically a function. And if you did help on this huge thing, it would tell you that you would need to supply it with two arguments. And these are the arguments to this function. Does that make sense to people over here? Might have been standing in the way. So for the various different keys to this dot quantities dictionary, they might require different arguments. So what I hope you learned in this quick overview of getting into your data is you've learned how to inspect the values in various locations in your data. You've learned how to use derived quantities. It's given you a sense of a way to explore your data, and I've hopefully shown you that it's really easy to get complex analysis out of your data using these types of operations. So with that, thank you, and any questions?